Hi, my name is Ken Masterson. I wrote a microbiome prescription website, and today I want to take you through a new feature which is taking a bit of time to get working, but it may also be a help to identify things. As some of you know, I've been slowly trying to extract as much information as I able to from a 16S microbiome sample or any type of microbiome sample where we have details. The purpose of it is to hopefully see deeper into what is happening in the microbiome, especially in terms of medical conditions or symptoms. So this is one of these experiments, literally experimental display of data and explaining how I'm getting the data from it and speculating on what could be done with it to be useful things. So the first thing is, let's take a look at our model of what's going on. We have intestinal microbiome, which has things being produced in it by one bacteria, which is now being consumed by a different bacteria. So they are busy interchange. View it as being a city, and we have local consumption and local use or local production. So the two of them goes around and around, and it's all within the city. However, cities also get products coming into it and products going out of it. So what we're going to try to do is capture all of the chemicals, all the components in this whole complex system, as in what is being locally consumed, what is being locally produced, what appears to be going out, and what appears to be coming in. Now, how in the world do I do that from a bunch of bacteria? The method is very simple, but it's somewhat lengthy. We have our 16S or other type of microbiome lab results, which executed on it, and now we get a list of bacteria with a count, keyword count of them. From that count, by the particular species involved, we go over to the Kilda Encyclopedia of Gene Genomics and see which enzymes are in each one of the species. Now that we have all the enzymes for a particular species, and we have the count for how many of a particular species we have, we can now estimate how much of each type of enzyme is present in the microbiome. Then we go back to KEGG, and from KEGG we know which compounds or chemicals are consumed or substrate, to use their term, by the enzymes and which are produced by the enzyme. So we now have input and output. And thereby we are able to say, okay, here is a compound and we have a abundance of a particular chemical being produced. Doesn't mean it's in balance, but it may mean that a lot of the chemicals isn't being used in the microbiome, but is going on and being entered into the body system. Or in some cases, we may not find anything produced, but the substance being consumed in large quantity. And that would imply that the chemical is perhaps coming in from the body itself. Take something like inulin, which could be coming in and feeding a process. So that is basically the overview of what we're doing and what this new page will show. So let's hop over to look at the new page and how you get to use it. So we're over on the microbiome prescription website. I'll do a login and I'll go over and use the biome example login. So people who can actually do it themselves, we go in there and we go over to 16S samples. And now we'll find we have component analysis. And click there, we see right here, it says compounds, producers, and consumers. We go in there and we get the numbers, and you notice the percentiles are missing here, and that is intentional because it takes a while to compute them. And so on upload, it is just burning too many cycles, and few people are actually probably going to be using it. So I've deferred it, and if you want to get them calculated, which you should if going to this page, just click here And then we have a bit of a long wait because it does. There is actually not too bad. What we have up here at the top is what we're talking about is 48, almost 45,000 different compounds. And you're sort of going, 45,000 different compounds? Yes, overwhelming. But what we do have, if we scroll down, is we can have things there. And here we have the usual name. Here we have other chemical names. Here we have the chemical compounds. Some of them are doozies. And now we have percentile. And in some cases you find things are same numbers in and same numbers out and same percentile. That's good. Other times we find that there is a difference between ratios. Other times we find the same. And the ratio is the ratio of actual raw count. And then we have a percentile ranking. Like, for example, in this case, we are typical for producing this one, but for consuming it, but we have a very high number of that one. Let's take a look at a couple of things that some people may be interested in, such as H+, hydrogen ion, and we find that we have a high percentage of consumers of it, but we have even a higher percentage of producers of it. And the actual ratio between the two of them is 8:1, which it would imply that a lot of the production is going into the body and being used by the body. So that is an example. We could do something such as SO2, or let's just do sulfur. Nope, nothing there. Let's try something like nothing. I was looking for melatonin, but that's what is. Oh, I know what. DAO DYN. 1 second. I'll go and get correct spelling. Okay, I was thinking dealing with mast cells, so let's go over and look at histamine or histidine, and there we see how much is produced and how much is consumed, the ratio of it, and also the percentile ranking. And some cases we see things are nicely balanced, could be it's just being cycled. And we also notice we have 3 types of histidine, each with different numbers. One is we have low production but high consumption of it. So it's there. Chemical formulas are spelled there for clarity. But more important, let's go over to something like lactic acid, or here we have the official name from KEGG, which is R-lactate, but better known as D-lactic acid or L-lactic acid. And what we have is we have D-lactic, which is the one that causes brain fog, tends to, in this case, has a relatively low percentile, and the consumer says high percentile, which means chances are D-lactic acid is being well cleared by the system in the stomach. And over here we have the regular one, and the 2 numbers are close in absolute count and also in terms of percentile. So they are probably in balance. And then we have some okay, not oddball things. So what we have is we have all of these items, and we have, depending on what is in your sample, we have 593 items which we have readings on, although we have 9 times the number of possible things. And that is usually because we are dealing with a nasty thing called sampling. The bacteria must be measured by the lab. Many labs only measure certain species and do not measure other species, which means you're going to get odd numbers. And the genes have to be known. The particular strain has to be fully sequenced. Not all of them are. So that we are spotty in our data there. Hence the numbers being produced are spotty. Hence needs to be taken with a big grain of sodium chloride, i.e. salt. We also make assumption that 1 unit it's being produced per bacteria, which is a erroneous one. But since we don't have the data to be precise, we make that as an assumption and work on it, which is why the percentile ranking actually becomes more important than the actual count, because with the percentile, we're applying the same assumption and you can see where you rank. If you click on that, you get over to the KIG and you get all sorts of information about it. And basically that's it. We have things, some cases you'll come down and you will see that they are producers, and that the ratio, that the percentile is actually comes in as a 0, because we have nothing which is actually, well, okay, there's the cases where you will have data in one and the other one may actually end up being a blank or something along that line, and it's because, again, of the spotty knowledge. Okay, so that's basically it. A few things I wanted to double check, but I think that will give you an idea of what the new features are.